Alright, so as we start looking at trig, the first thing to understand is that trig is all based on angles. We're looking at angles and how sides, particularly in triangles, but even in other shapes, how sides are related to each other. But we want to talk about a little bit about angles here before we actually get into using sine, cosine, and tangent. So a couple things we're going to talk about today are some terms that you need to know, and also some different ways of measuring angles. And then we'll finish up by talking about arc length a little bit. Okay? The first thing that you need to understand is that we work with angles in the coordinate plane, and we put them in what's known as standard position. Okay? Standard position. Now, make sure we understand what standard position is. First of all, the vertex has to be at the origin. Okay? It has to be at the origin. Also, the initial side, or the side where we start from, has to be on the positive x-axis. Okay? So you have to have a vertex at the origin. You have to have one side on the positive x-axis. The other side can be anywhere. All right? We rotate from that positive x-axis to what we call the terminal side, and we'll refer to that term throughout here, the terminal side of an angle in standard position. Okay? Now, one thing that you didn't run into in geometry is the fact that angles can actually be measured negatively. Okay? So, it all depends on which way we rotate from that positive x-axis. If we rotate up or counterclockwise, we have the positive angle. Okay? If we rotate down or clockwise, we have a negative angle. Okay? Clockwise just means the same way the clock goes. If you're not familiar with that term, counterclockwise is backwards. Okay, so we have standard position. We've got to know what we're talking about with standard position here. A second thing, and this is a direct outcome of the fact that we can measure either positively or negatively, is the fact that we could have an angle drawn in standard position, let's say like this, but that actually could be measured in infinite number of ways. Okay? I could measure this angle, first of all, by just rotating in the positive direction. Those of you who aren't with me here, which is a few of you, who are so engrossed in your computer you don't even realize I'm talking about you, thank you. Okay? If you miss this, you're going to be really lost. So you need to focus here. Alright? I can measure this rotating in the positive direction. I could have this exact same angle, and I could rotate in the negative direction. Okay? And those two angles there, even though they look the same, we have two different measures, we would call those coterminal angles. Okay? Here's another example right here of coterminal angles. Okay. Rotating in a positive direction or a negative direction. Now, you might remember I said that there's an infinite number of ways I could measure this angle. Okay? This is only two. So what's another way I could measure this? What could I do? What do you think?
Pass, I'm not sure how that exactly phrased, but if you're measuring it negatively, you could go around to more than 360. You could circle it again, I guess.
Okay, so if we went around a full 360 and then went to the terminal side, yeah, okay, that would be a coterminal angle. Likewise, in the positive direction, we could do the same thing. We could go around a full lap and then go to wherever that angle is. All right? So, if this original angle measured in the positive direction was, say, 200 degrees, okay? You know that a full circle is 360 degrees, so what would it be if we measured in the negative direction?
60.
It would be what? Negative 160, okay? Now, if we took a full lap around, a full circle around, and then went negative 160, what would that be?
Negative 520.
Yeah, negative 520. Negative 360 and another negative 160 would be a negative 520. Okay? If we went in the positive direction, a full 360 and then the 200, we would have gone 560 degrees. Okay? Now, all four of these angles are coterminal angles. And this is why we often will say that the measure of this angle is 200 plus 360n, where n is an integer. Obviously, you wouldn't go around a fraction of a circle because you wouldn't end up in the same spot. So n has to be an integer. Okay? Or you could say n is an element of, there's the symbol for integers. Okay? Now, does that make sense so far? Okay. We're going to use coterminal angles, and we'll use another variation of angles here in the future as we move forward. But you might say, well, what's the point in getting, 560 degrees or something like that? One of the applications is in like programming things. Okay, whether you're programming a robot in a manufacturing plant or something like that, if you want it to rotate a certain number of times and end up at a specific angle, okay, in the programming it doesn't say rotate X number of times, it'll say rotate this many degrees. Okay, so if we want it to spin around twice, we'll say rotate 720 degrees. Okay, so that's that's one element where this can be used. It could also be used to like see how far something will wind up if we turn it so many times. Okay, we can actually use a formula we'll look at later for arc length with an angle that's more than 360 degrees. Okay, so we'll get to that later. Now, another thing that I want to look at, another thing related to angles is how they're measured. And there are two elements of how they're measured that I want to take note of here. First of all, this is something that's actually used a lot in real life, is degrees, minutes, and seconds. Okay? Degrees, minutes, and seconds. And you'll see on your calculator it'll have this DMS and DD. Okay? DMS stands for degrees with minutes and seconds. DD stands with degrees with decimals. Okay? Now, we're used to dealing with degrees with decimals. 16.811 degrees. Okay? You've probably seen, however, something like this. Yeah, latitude and longitude. All right? When we deal with latitude and longitude, like with GPS coordinates. Okay? Latitude is this angle Notice we use the center of the Earth as our origin, and then we use the equator as our 0, and it's an angle either north or south of the equator. Okay? For longitude, we use, these longitudinal lines are what are known as meridians, okay? And this is an angle either to the east or to the west, a rotation east or west from what's known as the prime meridian, which is our 0. And it goes through Greenwich, England. But that's our longitude. You'll see, though, a lot of times, that longitude and latitude is given in degrees, minutes, and seconds. And the minutes and seconds are simply another way of expressing the fractional part of an angle. Okay? And the nice thing is here, if you think in terms of hours, minutes, and seconds, the conversion is really, really easy. Okay? So let's think our way through this. Let's say I want to convert this angle, 38 degrees, 42 minutes, that's what the little slash stands for, and 50 seconds, into an angle that's degrees with a decimal. Well, think about, how would you convert seconds into minutes?
60 seconds equals 1 minute.
60 seconds is 1 minute, so
50 over 60.
yeah, I'd put 50 over 60. So here I have now 38 degrees and 42 and 50 over 60. That'll be 5/6 minutes. Okay? Does that make sense? All right? Now, I know we're dealing with degrees, not hours, but the conversion is the same. There are 60 minutes in 1 degree. So how am I going to convert this 42 and 5/6 minutes into part of a degree? Divide by 60. All right, so I'm going to have 38, and I'm going to put the 42 and 5/6 over 60, and that's going to be how many degrees? Now, don't leave an answer like that. We'll find that's why this is called degrees with decimals. We'll go ahead and punch that into our calculator, and we'll get 38 point what? What do we have?
71.
0.71? 40 out of 60 would be 2/3, which would be 0.67, so that makes sense. Is he right? Hey, some of you had trouble on the test yesterday and you were asking me how to use your calculator. And I said, it's too late to ask that now, you should have practiced in class. Alright, like now is the time to practice using your calculator. Okay? Get your calculator out, practice, get it. Yeah. Oh, we're on 6. Okay. Did anyone get 0.71? You got it? All right. Okay. So, any questions about what we did here? Does that make sense? Okay. All right. Now, converting the other way, if we're given an angle in degrees with decimals, to get minutes and seconds, this would be just like converting a fraction of an hour into minutes and then into seconds. Okay? So, I know that this is going to be 16 degrees, but how am I going to figure out how many minutes there are?
Multiply the decimal by 60.
Yeah.
Multiply the decimal by 60. So 0.811 times 60, and you get what?
48.66.
48.66.
Would it be 48 minutes, 66 seconds, or just that?
Well, that's what we have to work through. We have another step we got to do. We do know that we now have 48 minutes.
So then 66 seconds till it will be.
Well, it can't be 66 seconds, right? Or we'd have another minute.
40 seconds.
That's 0.66 minutes. So it's 0.66 of a minute, right? So times 60 seconds in 1 minute,
It's 39.6.
39.6. Now, once you get down to the seconds, you can round to the nearest second. So we would say it's 16 degrees, 48 minutes, and 40 seconds. Okay? So guys, if you can convert hours, minutes, and seconds to just a fraction of an hour, and you can convert a fraction of an hour to minutes and seconds, then this is no different. Okay? Yes?
Is it on?
Alright, any questions here? Comments, anything? Okay. Alright, so that's one other way we can express an angle. Another thing that we can do with our angles is actually convert it to a whole nother measurement system. Okay? A whole different unit of measure. Rather than degrees, we can deal with radians. Okay? Now, I want to define what a radian is. This isn't just something someone made up. It actually does have a mathematical basis. If we have a circle, obviously you know a circle has a radius. Okay? And if we draw two radii, we have what's known as a central angle. Okay? This angle right here is a central angle. Now, the piece of the circle that goes from where one radius hits the circle to where the other radius hits the circle is called an arc, and we measure that arc based on, we use a lowercase s, and that refers to the arc length. We'll see a formula for that next. So there's our arc length. This angle right here will be 1 radian, okay, if the arc length equals the radius. Okay? You adjust the angle until the arc length is exactly what the radius of the circle is, and you have 1 radian. Okay? Now, the interesting thing is here, there are 2 pi radians in a full circle. Okay? It's 2 pi radians for 1 full circle. Well, that means that pi, if a full circle is 360 degrees, pi is 180 degrees. Okay? This conversion right here is like one of the biggest things you need to memorize as soon as possible. Okay? Now, that right there is a conversion. And one thing that we need to be able to do is convert between decimals and, or not decimals, between degrees and radians. Okay? If you have an angle in degrees, you should be able to express what that is in radians, and vice versa. If you know what it is in radians, you should be able to express it in degrees. Okay? And you might say, well, what's the point here in doing this? One thing that radians allows us to do is it does allow us to express very, very small angles a little easier than dealing with degrees. If you think about it, 1 is a pretty decently sized angle, 1 radian. So if I have a 0.5 radians or 0.2 radians, that's going to be very small in terms of degrees. So you can express really, really small angles a little bit easier with radians than you can with degrees. But it's just another system we need to be familiar with. Now the conversion is like any conversion. We have this conversion factor, pi equals 180 degrees. And whatever you're converting to, that's what you want to be in the numerator. And then you're just going to multiply by that conversion factor. Okay? So, for example, here, if I want to convert 36 degrees to radians, what am I going to multiply 36 degrees by? What? Pi?
Pi radians over 180.
Okay. We can't just multiply by pi because then we're changing the value, right? We have to multiply by something that equals 1. Pi radians over 180 degrees equals 1. Because those are equal values, right? It's kind of like multiplying by, 12 inches over 1 foot or something like that. You had to multiply by two things that are equal, so because you're multiplying by 1. And now here, we put the radians in the numerator because that's what we want to end up with. Anytime you're converting, you put what you want to end up with in the numerator, you put what you want to cancel out. In this case, the degrees we want to cancel out, put that in the denominator. Now, another thing about these conversions is when you're converting these, you don't want to multiply by pi, and you don't want to get a decimal that's rounded. You want to simply reduce the fraction and leave it in terms of pi. So, if we multiply this, we have 38 pi over 180, and that actually reduces down 38 over 180 is 1/5.
36.
36, oh yes, sorry. It's not too many 8s there. 36 pi over 180, and that 36 over 180 reduces to 1/5. Okay? So this would be pi over 5 radians. Okay? And you would just leave your answer that way. Okay? Yes? Alright, does that make sense? Pretty simple. This you're going to be doing 16 of tomorrow. Okay? Some of them are really easy, but you'll be doing 16 of these tomorrow. Okay? Because we're going to use the unit circle and figure out what all of them are, what all the angles are in radians. So let's work the other way too. 12.56 radians is how many degrees? Okay? If I have 12.56 radians, what do I need to multiply that by? There we go, 180 degrees over pi radians. Because again, I want the radians to cancel out, so I've got to put those on the denominator. Okay? Now, this one you will just punch in your calculator. You'll use the pi button on your calculator to find what this is. And what do you end up getting?
719.63.
Anyone else get that? Okay. All right. Now, I want you to think about this because I want you to start relating this a little bit to the degrees to radians in your head. I want you to start being able to try to visualize radians. Okay? Pi is 3.14, right? So 180 degrees is 3.14. A full circle would then be
6.28.
approximately 6.28, yeah. So 12.56, what's 12.56? If a full
Double
circle, what?
6.28.
Well, yeah, but think in terms of like 6.28 was a full circle, right?
Just 2 full circles.
So this one's 2 full circles approximately. We used a rounded form. So I should get approximately 2 full circles in degrees, which would be
720.
720. And that's what we got. Okay? So, do practice. Do kind of keep in mind not just the pi's, but also keep in mind, like, okay, if pi is 3.14, you know, somewhere around 1.5 is going to be 90 degrees. Okay? About 1.57 or so. Alright, so try to make those connections in your head. Alright, the last thing I want to look at today. I know we're touching on a number of none of these are really, really difficult concepts, but they're all just little things that have details with them that you'll need to practice, okay? So the last thing I want to look at today is that concept of arc length that we saw up here, okay? Arc length is a lowercase s. And I told you that this arc length is part of the distance on the circle, or part of the length of the circle, the curve. And what do we call that whole distance? Our circumference, okay? So our arc length, let's define arc length. Arc length, which again is a lowercase s, is a portion of the circumference, and it's determined by a central angle. So we need to know a central angle in order to figure out what arc length is. And let's look at a proportion. Depending on whether you're dealing with radians or degrees, one side of this proportion will be different, but the other side will be the same. Okay? The arc length is going to be a ratio, a part of the full circumference. So think with me, see if you can come up with half of it. We're going to have S over what?
The circumference.
The circumference, which is, what's our formula?
2 pi diameter.
2 pi r, or pi times diameter, okay? Alright? Now, it's going to be in the same ratio as the central angle is to the full circle. So this is how we get this proportion here. It's either the central angle in radians over 2 pi, or the central angle in degrees over 360, equal to the arc length over 2 pi r. Okay? Now, as you can see, we could actually figure out a couple of different things using this formula. Obviously, if we knew the central angle and the radius, we can figure out the arc length. That's what it's primarily designed for. However, if we know the arc length and we know the radius, we can figure out what the angle is. This is where, like, the application to programming a robot or something would come in. Let's say we want it to move something a certain distance, and we know the radius, or the arm that it's moving, is so long. Well, we have to tell it what angle to rotate through in order to travel that distance. Okay? We'll get one where we find the angle here in a moment. Well, let's just start with the basic one here. We have a central angle here of 70 degrees, and we have a radius of 5.5 centimeters. So what would I set up to in order to find my arc length? Someone share what would our equation be?
S equal to radian times degree.
What?
S equals to radian times degree.
Degree over 360.
Wait, isn't it that S
We're-
equals R?
We're not going to use the radians in this case.
Use degree.
What did you say?
Doesn't S equal R, like you said before?
S only equals R if this is exactly 1 radian. If the central angle if I had, instead of 70 degrees, if I had 1 radian, then yes, you could automatically say S is 5.5 centimeters.
So what degree would 1 radian be?
I don't know how
You'd have to convert it and figure it out. But here we don't need to even think that hard. What could we do, Alexi?
It's S over 2 pi 5.5 centimeters is equal to 70 over 360.
Yeah, don't overthink, okay? S over our circumference, 2 pi r, equals 70 degrees over 360 degrees. Okay? Does that make sense? If you know the formula, we're just plugging it in and make sure you use the correct one of these depending on if you're in degrees or radians. Okay? So now we have, we could reduce that to 3/60. This is 11 pi. So we could write it as 77 pi over 36. But that doesn't really make a whole lot of sense in terms of centimeters. So let's go ahead and, what would that equal as a decimal?
You want us to use the pi button?
Yeah, use the pi button.
6.71.
6.71 centimeters, okay?
6.72 if you round to the nearest hundredth, excuse me.
Oh, yes, if you round. Which, by the way, on the test, actually, some of you did lose some points because of rounding. If I ask you to round to 2 decimals, that doesn't mean just chop off everything after the second decimal. It means actually round, okay? So just be careful with that thing, okay? So yes, 6.72 centimeters, all right? Now, here's the second one, this will be our last one, is what I was just talking about with our finding an actual angle, okay? Let's say we were constructing something, and this is a wheel that has a radius of 12 inches, and we need to pull something 38 inches, okay? So we have this rope that's attached to the wheel, or cable, or whatever you will, and we need to move this part 38 inches this direction, okay? Until it's, sitting over here. This is where we want it to end up, okay? Well, if we're programming this thing to move it like this, we would need to tell it what angle to rotate at, okay? Because that will wrap up 38 degrees of the cable, 38 inches of the cable, which will pull it that far horizontally. Does that make sense? Kinda? Okay? So we need to tell it what angle to rotate with, all right? So the distance we want to pull it is actually going to be the arc length we want it to travel, okay, 38 degrees. So if our radius is 12, how would we set that up in an equation? Oh wait, you gave the last equation. Can someone help us? Who hasn't answered one yet? Come on.
Oh,
We want the
do-
angle in radians, right? So
do we? Oh wait, in radian, never mind. Wait.
come on, look at the formula.
Degree over
It was right up
360
there.
equals the radian over 2 pi. Or wait, no. Is that radian?
It's going to be the radians, the angle in radians over 2 pi. That's correct. And that will equal 38 over, good, yeah, 2 pi r, so 24 pi. Okay? That make sense? Alright. Now, the nice thing with this is it's kind of easy to calculate, because if you just leave pi in there, we're going to multiply by 2 pi, and we get our angle to be The pi's cancel out. We have 38 over 12, 19 over 6. So 6 and 1/6 radians. Okay? If you simplify that 38 over 24 times 2, you'll get 19/6, or 6 and 1/6 radians. Not 6 and 1/6, 3 and 1/6 radians. Okay? Alright, so now we know how to program this machine to do exactly what we want it to do. Okay? Think about the cylinders in a car or whatever. You know, they have to move a specific distance up and down. Obviously, it's not telling it every time, but in order to figure out, in that case, in order to figure out what the radius would be to move it up and down exactly the right distance, they're using a full circle. They would have to figure out the radius in that case. Okay? And it's a little more complicated, but same principle. Okay. By the way, here you can see where, let's say we didn't have as big of a radius, it was just a small wheel, we could still use the same process, it's just our arc length would cover more than one rotation around. Okay? It might have to spin a few times in order to pull in a full 38 inches. Okay? So that's how we can use those angles, those coterminal angles, those angles over 360 degrees. Okay? Alright, any questions? Alright. There's a little bit here at the end talking about linear and angular speed. It's kind of an interesting thing here, but it's just a relation of our distance over time. Distance equals rate times time. So our rate is distance divided by time. And you can actually calculate it two different ways. You can calculate how fast something's traveling around the circle by using arc length over time, or you can figure out how fast the angle is changing. It's kind of an interesting one. How fast the angle is changing, so you have a central angle over time. Okay? You know, so if it opens up to 60 degrees in 3 seconds, you know it's changing at a rate of 20 degrees per second. Okay? And in certain cases that can be helpful. That's just kind of an application your book presented. I thought was kind of cool. Okay? All right.